Now we move on to other forms of industrial carbon materials, bulk industrial carbon materials. So you already, now we discussed a lot about graphite, and you know there are various methods of preparing graphite. You can make graphite from the pyrolytic carbon that you get from gaseous hydrocarbon precursors, and you can also convert carbons, convert polymers into graphite. Not all polymers, but some polymers via heat treatment, and you can also call it pyrolytic carbon because this is obtained after the pyrolysis of a polymer, which is also an organic material, not necessarily gaseous. Okay. Now, I told you before that not all polymers give you graphite. In fact, extremely few polymers yield graphite. Most of them would yield what is known as non-graphitizing carbon. And these non-graphitizing carbons are also then further classified or further divided into various various forms of industrially important carbon, and this is what we are going to start learning now, and then individually we'll talk about each one of these materials. Okay, so not all polymers give graphite, that you know already. Why does that happen? The question is why. So you know that if the polymer has some sort of chemical structure, let's say it has a semi-crystalline kind of layered arrangement, then there is a higher probability that you will get graphite out of it. But it's also sometimes even with certain layered arrangement, you don't really get graphite. So why does this happen? Number one, why do you get graphite or non-graphitizing carbon? Graphitizing or non-graphitizing, that is number one. And number two is also that sometimes you will see certain forms of carbons, they have a very flat structure, they have a very flat surface. So when they have a shiny surface almost. And on the other hand, you have something like coals and charcoal. Some of you even asked me questions about that. There you will have more porosity, and those carbons, they don't have any shine. They rather look like jet black. They absorb as much light as they can. So there are two mechanisms which are responsible for this. Now remember that graphitizing and non-graphitizing is more related to the chemical structure of the polymer, whether or not you have semi-crystallinity, and the flatness and certain other properties that we are going to discuss. That is more determined by this coking and charring mechanisms. But now we are basically talking about the mechanism of polymer to carbon conversion, and then that will then we will learn about other carbon materials. Okay, coking. What is coking? Number one, you know already about coke, needle coke, which is a common precursor for industrial graphite. But needle coke does have graphitizing, so it has already certain graphite crystallites, although they have impurities, but they can lead to graphite formation. But needle coke is something you know about. However, there are also some coke. So coke is not just one thing. Coke is a range of materials again. Cokes can also yield non-graphitizing carbon. So that depends on what is the precursor you used for making the coke. Even within the petroleum coke, you may not always have all same kind of coke. So for example, in the case of pitch, you learned that there is an isotropic pitch and there is a mesophase pitch. One has graphitic crystallites and other doesn't. Other gives you isotropic carbon and one gives you anisotropic carbon. So same thing happens with coke. Not all of them will give you the same type of carbon. Then why do we call them coke? Because they are formed by the coking mechanism. And what is this coking mechanism? You know that your carbons are made from organic materials, and if these organic materials, especially in the case of polymers, because now we are talking about solid materials, right? So if this polymer, after its complete degradation, which typically would happen at 300, 400 degrees or even before that in some cases, after its complete degradation, if this polymer undergoes a semi-solid or liquid-like phase, so if it softens, in that case, the carbon that you will get, how will it be? If you melt something becomes very soft, liquid-like, and then what will happen? It will try to minimize its surface energy and try to settle down. And now when it is settled down, then when the carbon is obtained from this material, then that will have a very flat and shiny surface. On the other hand, if this does not happen, as in the case of charring, your entire material, the structure is rigid. It stands standing there. Whatever mass loss happens has to happen through the same surface, but your skeleton of that polymer, it's like very rigid. In that case, what happens is you will rather get porosity in your material than a flat, shiny surface. Okay, this is how you you divide, you classify your material. So also on the next slide, I'm going to give you a chart. Here, these are just some of the possibilities when you carbonize any polymer. So you take, let's say, a cube of a certain polymer, put it inside the furnace. You have nitrogen flow, argon flow, or vacuum. So any inert atmosphere you have in your tube furnace. Now what did you do? You heated it up to 900. Let's say 900 is the minimum temperature at which you will get any reasonable carbon. Before that, you will have a lot of impurities. So let's say you heat this cube. Now what will happen? Is there just one scenario, or there are more than one scenario? So you are converting it into carbon, but what type of carbon? Scenario number one, whatever was the shape of your cube. So this is like, if you perform an experiment like that, this is what you will get. If you have the shape intact, then that is scenario number one. Number two, your shape slightly got modified or distorted. It's not even distortion, but it became slightly, it got flattened or became more smooth. Corners disappeared, something like this. So that you can see here in the structure number two. So this is the second scenario. The third scenario would be that your cube does not really shrink, or even if it does shrink, not very much. So in this picture, I have shown the exact same size, but you may have some shrinkage, but not very much. Why? Because all the mass loss that had to happen, that just created pores. So mass loss did take place. Let's say whatever carbon you obtain is lower than 30%, between say 10 to 30% of the original mass. But that mass loss does not necessarily, so either it will create shrinkage if it is uniformly, annealing of the gases and the tar-like things are uniformly annealing out throughout your material. Then it will create shrinkage. But if you have, pores being created, then the mass, wherever it is, the structure is very rigid. And now there is also this fourth scenario where you have rigid structure. So it's not shrinking and becoming smaller. You do have the rigid structure, but at some point the porosity is so much that now the structure cannot just remain intact anymore. So then you get something like flakes and powders, maybe very small fraction of your carbon. So these are the four scenarios that will take place. Now, among which ones will you call, what will happen if you have coking, and what will happen when you have charring? So maybe when you look at this picture, you can say number two is caused by coking. So your material, your polymer must have gone through some sort of semi-solid liquid-like state, and that is why you have these smoothening of the corners. But also number one can very well be caused by coking, because sometimes the polymer will not really become liquid-like, but it will just become semi-solid. Semi-solid is more like a rubber-like state, gel-like state. So you don't really lose the shape, but you do not get porosity, you do get shrinkage. Okay, now scenario number 2, 3 and 4, that is caused by charring. So there you may or may not lose the structure. You may or may not get some shrinkage. You may always get, but you will get a lot of porosity, and that is why your carbon will look very black. And now you can already imagine what are the properties you expect from these types of materials. When you have a very smooth and shiny surface, then of course being smooth and shiny itself is a very nice property. You have this very flat structures which can be used for a lot of applications. We are going to talk about the applications in detail. And if you have porosity, then this kind of material can have a very good absorbance for various gases, for various liquids, for impurities that are mixed in water. So you can use porous carbons for water filtration, for various different filtration applications. The fourth type of carbon, when you have very small fraction of carbon, that Yeah, that might be useful, but you will never do that because then your process is too expensive to get very little carbon. So that you will most likely not do it. So these are the 4 scenarios. Now, for certain polymers, you may even have a combination of both. So you may, for example, initially the polymer does not become soft, but at certain higher temperature point, because of certain chemical reactions, it goes through some softening. On the other hand, it can also happen that the polymer does go through softening in the beginning, but later on it has a certain charring mechanism. So at some point the structure becomes rigid, and then you only get shrinkage. Or maybe you even may get some porosity. So, but these cases are rather rare. In general, you will have these 3 or 4 scenarios. Okay. Now, as I mentioned, then the mass loss can cause either shrinkage or porosity, or in some cases both. Okay. Now, how does porosity relate to density? When something has more porosity, it has less density. Okay, that is very clear. So when you have these coked carbons, carbon means whatever is prepared by coking, then you're going to have it very dense. So even if that is a very simple experiment. If you have a liquid and you pour a liquid inside any pot or something like that, you will have whatever shape the pot has, the liquid will take, and then that is the shape that is going to be your later on. That is what you're going to get with a very flat surface, atomically flat, and with high density. But in the case of chars, you're going to get more porosity and therefore less density. Okay. Now, in some cases, if you already make your polymer structure porous, like as I've shown here, this also you can do. So there are many things you can, when it comes to manufacturing, we will talk about that. Then you can play around with these, with the fact that, how much does your polymer soften during its carbonization, and does it give you graphitic and non-graphitic carbon. So you can already also make your structures porous, and then you see what happens. Now, in this case, whether you call it coking or charring, this is actually coking that is happening, because the porosity is not because of the what happened during carbonization, or because of carbonization. The porosity is something we already had in the polymer structure itself. In fact, the entire thing shrank, and that is why even the sizes of the pores became they changed, they were modified because of the shrinkage of the entire structure. Okay. Now, here in this slide, then now I have a little more, the classification, nice diagram which will tell you I have not written the names of the polymers, but I've just written, what mechanism will give you what. Okay. So, coking mechanism, polymer goes through certain softening. Okay. This can give you graphite. We talked about it, right, from PVC. Okay. So, this will give you pyrolytic graphite. What you can do with this, you can make highly oriented pyrolytic graphite after further treatment, or even when you are when you have very high heat treatment temperature, then you can get highly oriented pyrolytic graphite, or you can also just stop at pyrolytic graphite. Okay, here I have also mentioned that by hydrocarbon pyrolysis you can get it. So pyrolytic graphite, although it's not a part of this particular diagram because it's polymer, but I just showed it because HOPG can also be obtained. Now, coking will also give you some cokes. But as I said, cokes are, this is again a range of materials. It's not one unique material. Some of them will give, they will give you different types of carbons. Okay, so you get cokes by coking. Some cokes, for example, needle coke, will definitely give you a graphite. So I've classified these pyrolytic graphite and cokes. Some cokes which will give you graphitizing carbon. Okay. Now, from this process of coking, one more very important material that is industrially important, that is also used in micro and nano fabrication, and that is going to make at least a few of our lectures. This material is known as glass-like carbon, commonly known as glassy carbon. Although the IUPAC name is glass-like carbon, but commonly it's known as glassy carbon. Okay. Now, this is again another type of carbon which has a very flat surface. And since it is prepared at very high temperatures, it also has very high purity, and interesting electrochemical properties despite the fact that this is not graphitizing. In fact, no matter how high you heat it, at to what temperature you heat it, 3000, but it will never convert into graphite. In fact, this is one of the most important non-graphitizing industrial carbon materials. Okay. So yeah, this is an image. It looks something like this. I mean, basically it is just a plate of carbon which looks very, very shiny and flat, maybe slightly darker in color compared to graphite. So graphite is this graphite, you may say it's black, I call it like darkest gray. But this carbon is black. So now I actually, after seeing so many carbon materials and after reading about them and doing experiments, I can differentiate the shades of black. But you don't need to do that. They are typically, most of them are black. Darker black and lighter black and shinier black, and something is very dark, darkest gray color. But basically glass-like carbon is slightly darker in my mind compared to graphite. But it has a very shiny surface. Okay, and it's a very highly stable material, very interesting material. We'll talk about that. Okay, now let's come to charring. Charring gives you something called activated carbon. You must have also heard about activated carbon. So activated carbon, actually, if you buy in the market, you will buy these, you will be able to get something like this, which looks, you can say it looks like coal. You can say also that you have these, cylinders of activated carbon. It has no shine. This is the first, this is how you recognize it. It definitely has no, so it absorbs as much light as it can. So it looks, well, it looks blacker. But it has also, you can buy pellets, you can also get powder of activated carbon, and you can get these kind of cylinders. Basically, the reason of its color and its lack of luster and so on is that it has a lot of porosity, and activated carbon therefore is used for a lot of absorbent applications. And water filtration columns is one of the most important applications. In fact, if you have a water purifier at home, most probably you have the column that you have inside it. Most likely it has certain form of activated carbon filled, maybe in the powder form. So you have these columns of activated carbon, which which feature great absorbance. Okay, and after that, whatever there may be a lot of these char-like materials. So for example, even charcoal, whatever you get from the wood. So if you don't have very high temperature heating, in that case you will always have a lot of impurities in it. So also when people are performing waste treatment, so they take a mixture of a lot of things. Whenever you have a mixture of, let's say, plastics as well as you have some wood, and now you heat them all together. Now the wood type materials, cellulosic materials, will typically undergo charring. So, and synthetic polymers will typically undergo coking. So this is also, again, it's a rule of thumb. It's not the case with all the materials or all the polymers. Certain synthetic polymers can also have charring or a combination of coking and charring. But as a rule of thumb, natural polymers like cellulose rather will give you, chars. So they will undergo charring mechanism, and synthetic polymers coking. Okay, but if you have something like waste, urban solid waste, what is called, so, which is a mixture of a lot of polymers. You have a lot of polythenes, household polythenes, and plastics and so on, as well as you have, you may have some wood, or you may have some paper and things like that. So in that case, the mixture that you're going to get, if you don't, you cannot really recognize whether it is coking or charring, what mechanism, it's like a mixed carbon material. In that case, you will just call it a char. So whenever there is a sort of low purity carbon, or you don't know the exact composition of that polymer, do you have any metal impurities in it or not, which can very well happen in the case of waste materials, or waste derived carbon, let's say. So if you don't know much about it, or you cannot say 100% this is this is the purity, this is the type of carbon, then you just call it char. So low purity chars I have segregated. This is also, we would call it either charring, or we can also obtain it with the a combination of coking and charring. Okay, so now interestingly, these four things that you know, the green boxes, they are non-graphitizing. You see that coke I have mentioned in both graphitizing, non-graphitizing, because you can have both types of cokes. Glass-like carbon and activated carbons, these are definitely non-graphitizing carbons. And we are going to learn in detail what do we mean at a microstructural level. What do you call a non-graphitizing carbon? So you understand the general definition is that whatever is not graphite but it's a high purity carbon, then you can call it non-graphitizing carbon. Low purity carbon you will generally either just call char, or even when you say coke, coke is also a term that is used for low purity carbons, because not all cokes are more like raw materials for preparing high purity carbon. So coke and chars are not necessarily very high purity materials or high purity carbons, but glass-like carbon, activated carbons, so typically they do have high purity. And of course your HOPG, the highly oriented pyrolytic graphite, that you know has very high purity anyway. However, at microstructural level, what is the difference between these two types of carbons is what we are going to learn, especially the non-graphitizing carbon. Okay, so now the fundamental definition at large scale is, even if you heat, no matter how high you go, up to 3000 degrees, you will not be able to convert these non-graphitizing carbons into graphite. Why does that happen? Is because from the beginning, when they were forming, whatever, whether it was coking mechanism or charring, when they were forming from the polymer, some curved carbon structures were formed. And these curved, so once you have fullerene, for example, they may be curved carbons, not completely spherical structures, curved structures, tube-like, or just some very, very wavy sheets of graphene. Now, however, the point is that once a completely curved or highly curved structure or a complete sphere is formed, that requires a very high energy to open. So the energy of formation of fullerene itself is pretty high. Once it is formed, because of whatever reasons, whatever that depends on your chemical structure of the polymer. Maybe that was the most suitable structure at that point. So you got these very highly curved or completely spherical structures in the beginning itself. And now the energy to open those fullerenes and convert them back into graphene-like sheets is going to be very high. Sometimes it is not just possible to do so. And that is why they will never, no matter how high you heat them, they will not become flat again. They will not make the ABA crystallites again. They will remain curved. And that is why you're going to have a very complex microstructure. If you look at these materials, or look at non-graphitizing carbons, what are you going to have? You're going to have a lot of curls, a lot of folded structures, a lot of curled structures, and some completely closed structures, and so on. And that they can also be of different sizes. Some of them may be very small, some of them may be very large. So you can never really define a crystal structure for this kind of material. So despite the fact that you have all these, you can call them graphene sheets or graphene-like sheets, because graphene we call only when it's single layer and when it's defect-free. In this particular case, you're definitely going to have defects. Defects are here point defects, non-6 membered rings. So you're definitely going to have them. That's when you're going to get the curves. That is what is the reason for the curvature in these carbon structures. So you're going to definitely have these structures. So now it's a complicated thing whether or not you should call them graphene, because they are these, you can say these are sp2 carbon sheets, but even that is not a perfect way of describing it, because sp2, well, you don't know, because these are curved carbons, you may have sp2 plus n type hybridization. But you understand what I'm talking about. It's these graphene-like sheets, but with a lot of non-6 membered rings, and that is why you have the curvature. You may have these sheets in a variety of sizes. And you may also have some completely closed structures, and all of these together then will make your non-graphitizing carbon, which is glassy or activated. Okay, now glassy and activated also. When the microstructure is so similar, then why are they different in terms of properties and in terms of physical appearance? Their mechanism of formation was so different. One was prepared by coking and the other one was prepared by charring. So one has pores, one does not. That already makes a lot of difference. So this is what we are going to learn in the, now we are going to learn maybe activated carbons. I don't know, I'm not going to cover them today, but this is just the sort of background. We are going to learn about all these things. So here on this slide, I have shown you now, just, for today, this is good enough that you see the microstructural difference. So you see these are three transmission electron microscope images. In each case, the scale bar is 5 nanometer. First one indicates graphite. Now you know that what is the layer separation in the case of graphite? You have what is 0.335 nanometer. Now in the case of other carbons which are graphitizing carbons, they look like this. This is like the second image. So you can already see that there is a possibility. There is a possibility that this material can become like the first image. It can convert at higher temperature. But if you had the non-graphitizing carbon that you see in the image number C, no possibility. You can see already that it is kind of all entangled. Forget about it. It's not going to open and then give you graphite. So these are the three images that will give you some impression of what is a graphitizing carbon from a polymer and what is a non-graphitizing carbon. Okay. Now, in the case of non-graphitizing carbons, however, you may have what is known as a short range order. What does that? So here, I don't know if you can how clearly you can see from this image. You have 2 or 3 layers definitely organized on top of each other. You just do not have a larger stack. You may have a few. In fact, as you keep on heating the material, so keep on increasing your carbonization temperature, you will also get some increase in these stack thicknesses, or the La also, the crystallite size as well. But you will not get complete graphite. So the entire material, it will, with the temperature, it will definitely gain more and more order, but you will not get complete, graphite. And that is why they are called non-graphitizing carbon. So you may have short range order, means small crystallites that you can have, which can also be measured using, for example, X-ray diffraction techniques, or in the TEM micrographs. That these are the TEM micrographs. So you can definitely also see it here. You can also do Raman spectroscopy characterization techniques. We are going to learn in some other lectures. Raman spectroscopy tells you what is the fraction of crystalline or disordered compared to graphitic and disordered, 2 types of carbons it will tell you. So we will talk about that. The point is that these as you increase the temperature, you may get more and more crystallinity, more and more order in the material, which is measurable. And in fact, that is how these techniques become very important in graphite preparation. That is why the heat treatment temperature becomes very, very important in the case of all carbon materials. But if you think of it from the industrial viewpoint, when you increase the heat treatment temperature, that also really increases your cost. 3000 degrees, just think about it. You're using some coils, or you typically using whatever joule heating process. If you heat something up to 3000 degrees, that definitely adds to the cost of the material. And that is why also there have been a lot of processes that may, or at least people have tried out, to reduce the temperature of your of carbonization, such that the cost can be reduced. But of course, the higher the temperature, the better the material. At least as on date, that is the status, that you have high temperature carbons are more expensive and you have better crystallinity and better purity. Because let's say if you want to do catalytic graphitization, you can add some catalyst which may reduce your final temperature a little bit, but then later on you have to remove that catalyst particle from the material. So you ultimately end up adding one more step. And despite that, you may not really get very high purity in your carbon. So all these things add to the cost, and that is why when it comes to industrial carbon materials, still the good carbons are prepared at very, very high temperatures. And of course, at every step, we are going to do a lot of characterization to know what is the quality of our carbon. And the quality is always measured in the case of carbons at least these sp2 type materials, or materials which have disorder, mixed allotropes, and so on. Also, in the case of curved carbons, the better electrical conductivity, better mechanical properties, etc., are all measured based on the crystallinity. Okay. Now, if you, whenever you're doing these any characterization, if you get a sharp peak, for the X-ray diffraction, for example, if you get a sharp peak, that means you have these 00L planes that we talked about. So if you get sharp peak for that, then you have the the material is closer to graphite. Or it has at least graphitic crystallites, a lot of them. But on the other hand, if you get a broad peak, which you would call a hump, that indicates that you don't have any specific crystal plane. That indicates that you have variable bond lengths throughout your material. So when you have curved structures, when you have certain molecules that are under strain, and you have some of them are very small, some of them are large, some have certain stacking, some don't have certain stacking. So altogether you will get a range of bond lengths. And that is why when you're doing its characterization, you will never get one specific value. You'll always get sort of a range of values for everything, and that also then influences the properties. When somebody asks you what is the electrical conductivity of glassy carbon, then you will always mention a range, because, well, that will depend on the exact heat treatment temperature of your glassy carbon, exact graphitic content, exact fraction of short range order. All of these things will then determine the properties of these non-graphitizing carbon materials.